Electromagnetic radiation, or light, is waves of oscillating electric and magnetic fields. We symbolize an electric field with a capital E, and for obvious reasons we symbolize a magnetic field with a capital B. Actually, no, not for obvious reasons. In any case, magnetic fields are symbolized by capital B. The source of all electromagnetic radiation is vibrating electric charges. The great physics teacher Paul Hewitt, I think he's great anyway, gave a nice example, an analogy to this idea, where he talked about putting a stick into the surface of a pond and shaking the stick, and waves emanating out from the source of that vibration. If you take a charged particle, like an electron, and wiggle it back and forth, back and forth, back and forth very quickly, what emanates out from that charged particle that is moving and accelerating is light. So all light consists of oscillating electric and magnetic fields that are at right angles to each other. Here I've represented the electric field as going in an up and down sort of transverse wave, and the magnetic field as going into a snaking along side to side wave, and the direction of the disturbance is at right angles to both of those. In the case of this one on the screen, to the right. Characteristics of a wave. Light is a transverse wave, and we can think of it as consisting of crests and troughs. That distance there between adjacent identical portions of a wave is called the wavelength, which is symbolized by lowercase Greek l, L for length, that's a lowercase Greek lambda. And the height above equilibrium is called the amplitude. These are just generic characteristics for any transverse wave. The frequency of a wave is the number of cycles per unit time, usually seconds. The number of cycles per second, or the number of wiggles per second. And the unit typically for light definitely is hertz, which is cycles per second or wiggles per second. Sometimes a hertz is represented by a seconds to the -1. Those are equivalent units. So if you see something represented as so many seconds to the -1, that's the same thing as so many hertz. The electromagnetic spectrum contains all of the types of light that vary according to frequency and wavelength. So I've represented here many of the different types of light. Radio waves, which have very long wavelengths, and cosmic rays at the other end of the spectrum, which have very short wavelengths. The differences in the lengths of these wavelengths is much greater than I'm able to show in this picture. I'm just trying to give you a flavor for the idea that radio waves have long wavelengths, and at the right end of this picture, very, very short wavelengths. The visible spectrum, that is, the bit of light that our eyes are sensitive to, is a very narrow band of the spectrum. Just like there are sounds that other creatures can hear but humans can't, there are many, many varieties of light, many frequencies of light, in fact most of them, that our eyes are not sensitive to. So on the left end of the spectrum we have large wavelengths, on the right end of the spectrum small wavelengths. On the left end that represents low frequency radiation, and on the right we have a high frequency radiation. Radio waves thus have low energy, and cosmic rays, gamma rays, those kinds of things have high energy. You can think of it, if you had a rope attached to a wall and you wanted to shake it up and down to look like what's on the left side of this picture, you wouldn't have to shake it up and down very quickly. Up and down and up and down. You wouldn't have to put a lot of energy into it. If you tried to make that rope look like what's on the right side of this diagram, you would have to shake that thing down in a hurry. It would take a lot of energy. That helps us remember that the right side of this diagram has lots and lots of energy. The visible spectrum, we said it's a very narrow band, ranges from about 400 to 750 nanometers, a very tiny portion of the overall spectrum. Final thoughts on light as a wave. 1. Light, or electromagnetic radiation, consists of oscillating electric and magnetic fields. The source of these oscillating fields, and therefore the source of light, is wiggling electric charges. 2. The wavelength, lambda, of a light wave is the distance between adjacent crests. The electromagnetic spectrum shows the various types of light.